colloquium today. This is going to be, I believe, the last colloquium of the fall semester. And I am delighted to introduce today's speaker, who is one of our own, Professor Donna. She teaches in the Mathematics and Statistics Department at American University, and where she has taught for 8 years. Prior to teaching here, she taught at 6 different colleges and universities, and has also taught several computer science courses. She lives in Tacoma Park, Maryland, with her husband and their 3 sons. Her favorite area of mathematical research is recreational mathematics. Today, she's going to talk to us about the analysis of a game called IQ Link. Go ahead, Donna.
Thank you guys for coming. I'm so excited to see you guys. And wow, okay. So I'm going to tell you about this game that was actually part of a, but when I went to the Museum of Math 5.5 years ago for one of their conferences. They have conferences on all the even years in August, and sometimes their conference grab bags have gifts in them whose sum total value is greater than the cost of entry to the conference. So think about that for a second. And this was one of the toys in the grab bag. And so I immediately became addicted to it and wanted to study it some more. And so here's what it looks like. You obviously throw away the box, but you have a plastic case that you hold the pieces in, and it comes with a booklet. And I'll tell you more about that in a second. So in order to play, you have to open the booklet. There's 120 puzzles in the book. You pick one, and you put the pieces into the grid as is given by the instructions. Can you see my mouse if I point? Yes?
Yes, yes.
Okay, cool. Good to know. All right. So the idea is to place the remaining pieces into the grid correctly. This is a single player game, or you can call it a puzzle. It is a combinatorial game because there is complete information. It's not like a card solitaire game where you're hiding some of the cards. You can see everything at all times. There's no occasion for bluffing. You could easily adjust it to become a 2-player game if you took turns placing pieces. So it's a single player game, but you could change it. What I really wanted to know is I was trying to see if this game was something that would continue to amuse me after the initial phase, and I kind of wanted to peek ahead. And I wish there was somebody who could tell me if this game is essentially like a geometric version of Sudoku, or is it something fundamentally different? And by that, what I meant was, does the puzzlist have to truly address their strategy as they progress through the levels? Or is it kind of like a lot of Sudoku where you just have to keep trying and trying and trying until you're blue in the face? That's what I wanted to know. And I didn't want to sink too much time trying to figure that out by playing. Of course, I spent a lot more time because I wrote a program to do it for me. But this is, I want you to think of it like a movie review or a book review. This is a game review. And hint, I totally love this game. Okay, so this is the review I wished I had seen online, but it hadn't been written yet because it was waiting for me to write it. So what I did is I would come up with an algorithm and feed it into the computer. And meanwhile, I'm still playing with it by hand to get some intuition. So I'm getting this computer output, and yet I'm getting some intuition by playing manually with the game. And then I feed that insight from the computer and the manual insight back into the next level of making corrections and adjustments to the code. And so this talk is showing you some of those insights and some of how I optimize the code, which in turn gives insight into how the human interacts with the toy. And of course, the way the computer interacts with it and the way the human interacts with it are quite different, but there's a good deal of overlap, and it helps us understand the structure of the game. Don't worry, I won't ruin the game with you. I hope you all run out and buy one. I actually just checked on Amazon. They're less than $10. So they're really perfect holiday gift if you're looking for something to give somebody. I showed you this picture before, but this is just to give, to let you know Ralph Peters is the designer, and to make sure you know the rules. So when I say you need to fit the pieces into the tray correctly, first, I'm going to give you an anti-rule. These things on the board, the little raised circles, I'm going to call them spots or anchors. Those things, it's okay if one of those anchors still remains, that's fine. You do not have to use them all. However, the solution is unique, and that's actually something that helps you solve it. And only one connected graph is allowed. So I've drawn off to the left an example of a connected graph. Okay. So I'm going to put a live demo in at this point, and I have to share and reshare. Let's see. Okay, can you all see the puzzle? Can everybody see that?
Yes, we can see it.
Great. And so the first example, actually, I just laid out the pieces the same way they are on this this book. I just wanted to show you the one example I know of a configuration that is not a solution to anything. It was so nice that they put it on the front cover because it's not going to spoil anything. If you notice, these are two connected graphs. So this is not a single connected graph. So you notice this blue piece does not connect to this purple piece in any way. So everything that I'm covering up is essentially one graph, and everything over here is the other graph. They don't connect in any way. Does that make sense? So because of that, it's not a solution to anything. So when you're playing this game, you want to dump the pieces out, and then you want to open the book, and I'm just going to show you how to play the first, how to do the first puzzle so you understand the rules. So you look at the instructions, and then you set the pieces into the grid. So I'm going to go ahead and do that. So this piece, in fact, I just picked this piece. This is special because it's the only piece that has any kind of symmetry. It has this flipped symmetry, and it's the only piece that has this symmetry in it. I believe this is one of the pieces we have to actually place. And as you flip the pieces around, you'll see there's actually 12 different ways that each piece can go into the board, except for, again, the purple piece here can only go in 6 ways because of symmetry. But all the other pieces have 12 ways they can be placed on the board. And that's what makes it kind of addictive to me, fun and interesting. Okay, does that look right? Let somebody double check that for me. I'm going to look myself. Does the picture and the instructions match the configuration I've laid out? Does that look consistent to everybody?
It looks consistent to me.
It looks good to me. Okay, so if you're playing this game, which like you can play it with me now, somebody can just shout out, where do you think you would put this blue piece? Where do you think this piece should go? If you want to type your answers, Aleka can read them out loud, or you can just shout out to me.
Lower left corner.
Doesn't quite fit because it bumps up against the tray. Okay, so let's try another placement.
The lower right.
Okay, let's try the lower right. There we go. And in this early level of the game, all the first several games, if you can find a placement, it is correct. That's only true initially. Okay, so what about this pink piece? Where do you think it should go? Steve?
Yeah, again, wait, shoot.
Yeah, go ahead.
So let me see. Okay, I got a hook. So I'm going to put the hook over the green dude on the corner, then the ring and there. So lower left.
Yes.
All right.
Okay,
somebody
you
else.
got it now. What about
fun?
What about this alien? Yeah, go ahead. What about this alien shape? Where do you want to put it?
Oh shit, an alien. All right. Obviously, aliens tends toward the middle. So I would put him, the red dude hooking in with the green. And oh wait, shit, I don't have a.
Yeah, it works. It works good, Steve. You got it.
Yep. Okay. There you go. I got it.
Okay, cool. All right.
I'll
so
I'll let somebody else play.
That's
By the way,
totally fine.
You just sold
What?
5 copies of this game, so.
Oh, great, great, great. They're not paying me, I swear. So here's all the different games. And you can see that actually, when you get up to 120, the game only has 2 pieces in it. Like the last several puzzles only have 2 pieces in them. So again, the difficulty level is ranked by the game developer. But I do agree with the difficulty, and I'll show you why. Because my algorithm solved them all, and I have some sense of the complexity based on what part of the algorithm was necessary to actually crack the puzzle. Okay, I'm going to go back to the talk, the slides. Okay, the rest of the examples are on the slides, but we're going to play it the same way. It's just a little bit easier to wield it in this format. So somebody want to tell me where the yellow piece probably goes?
I'm going to let somebody else have turns.
It's totally fine if you want to keep playing, Steve.
Should it go on the next to the purple one? Yeah, with the 2 loops around the purplish one.
Do you mean here?
Yeah.
Okay, that doesn't fit. Thank you for giving me that answer because I wanted to demonstrate this. So your eye will probably pick up incorrect things a lot. And so we're going to look for another structure that looks similar to that, but your eye is right. You're looking for the 2 little balls to put their loops around. So is there another place on the ball where another place on the board where that happens?
So the upper.
Anybody?
The upper
Yes?
right.
Yes, so that's where it actually fits. Good. So what happens is these the openings on the sockets are at specific angles, and it's very sensitive to where that opening is. That's what's going on. Okay, so what about pink? Where should the pink one go? Hey, Sarah, where should the pink one go?
I'm like in class and multitasking.
Oh, okay, sorry.
Too. Sorry.
That's totally fine. Anybody?
So I mean, it looks like it could go into the orange one on the bottom, right? But I'm not sure if that would.
Yeah,
work.
that's great. Okay, then what about the last one?
Then does it go around that center blank one then?
Yeah. Yay, we did it. Okay, now we're gonna upgrade to a slightly more challenging example, and I'm going to intentionally make a mistake, but I'm gonna see if you make the mistake for me. The first one we're gonna do is the blue one, and I'll explain to you why I picked blue, but somebody tell me where that blue piece goes. It's the one at the top. It says blue, purple, pink, orange, and then I'm gonna call the last one like lime. So that top piece, where do you think it should go?
Lower left.
Yeah. Now I'm not like really sure about this, and I'm actually 100% sure, not even just quite sure. And the reason is because of that linking condition. We have to, so I'm going to use my mouse here. If you notice, this blue piece does not actually link to the yellow piece, nor can it. The only thing that has remaining to link is this blue ball. And so it has to link into this red piece. It has no other choice because otherwise it'll be an orphan. So we have to use that blue piece here or we won't satisfy the linking condition on this puzzle. So we're 100% sure we've now actually just reduced the puzzle down a level. Okay, so now we only have 4 free pieces. Okay, where do you think this purple piece goes now that, we'll do that one next. Anybody want to take a guess?
Well, I only see one exposed ball, that pink ball on the top.
Okay, what is it? Yeah. And in fact, it does go there. And the thing is, that purple piece could go just about anywhere, right? But there is this need we have to connect this this aqua piece to this pink piece. Now, it's not as strong as the other need, because in theory, we could wrap all the way around the graph this way to get those pieces connected. However, since they're adjacent pieces, it's highly likely that they'll be connected with an intermediate piece. So this is, I'm at the point of making this move, I'm basically 95% sure that that's right. Okay, now the next move is going to be incorrect, but I'm going to put it where it seems like it should go. It's going to feel right, but it's going to be wrong. Okay, so where do you think the line looks like it should go? Steve, this one's for you, because if you get it wrong, it's right, and if you get it right, it's wrong. Where do you think the line one goes? That's a trick question, because I'm trying to get you to fall into my trap.
Well, I think
right?
you're baiting me to put it up here, up in the right-hand corner. So
up here?
Yeah, that's the bait.
Yeah,
but
that's
then
the
I'm
bait.
blocking.
I totally, yeah, but the thing is, I told you that's wrong, right? So I'll tell you why it's wrong. Thank you, thank you. Okay, so if you make that move, the only move
block,
that you,
right, you can't connect.
right, because you one there and the pink doesn't fit. So you got to back up. Now, this time we're going to do it right. Let's place the pink one first. If you're going to place the pink one next, where do you think you might like to put it?
I think the red guy goes in that corner and the pink, shit. Okay, 1, 2, 3.
It's okay. It's not a problem. Just pick something. So where do you want to put the pink one? You want to loop that pink loop, the pink socket around what ball joint? Or not at all? Where do you want to put it?
Well, you really only have one ball joint to link it on, and that's the
yeah, you do. And it turns out to be correct. It's okay. So it actually leaves enough room to put. Right. Okay, yep. So it often happens with these games. Everything, once you get only 2 pieces left and you've done it correctly, they just fall into place really easily. Okay, so game over. Now we get to talk about it. So you do, in fact, need to have the book open. This is the only thing I don't adore about this game, is that if you're playing, you have to have the book open so you don't, when you're doing the backtracking steps, you don't dismantle part of the original setup. That's the only problem. Okay, but other than that, I love this game. And the early puzzles don't require backtracking, so it really draws you into the game pretty quickly. Okay, so the first idea I had when I first got home from the conference, I'm like, I have to understand this game. I have to understand what makes it tick. I got to understand it. And so my first idea was to split up the balls and sockets and do some kind of naive count. And so there's actually 6 full circles. There's 14 normal ball joints. There's 2 elbow joints. And those elbow joints can only be either unmatched or they can fit inside the wide socket. So the elbow joints, again, they can either be completely unmatched or they can go inside the wide socket. And then I have 13 normal sockets. And so I'm going to combine both kinds of balls and both kinds of sockets to make the counting simpler. But out of the 24 anchor points, we have 6 full circles, 14 sockets, and 16 balls. So what you end up with is, since E isn't actually an unknown, it's just, I just put it there. So you have 4 unknowns and 3 conditions, which gives you 1 degree of freedom, and you're only doing non-zero integer solutions. So you really only end up with 3 possibilities. But one of those possibilities doesn't actually occur in the gameplay. So you're either going to have 0 or 1 empty spots on the board. In terms of gameplay, what that means is you can't have more than 4 unmatched balls or more than 2 unmatched sockets, or it's time to turn around and try something else. And just knowing that is kind of nice, so you don't get yourself too deep into something that's not going to work out. Make sense? I'm looking at Alika, she nodded, so I'm going to go to the next slide.
So,
Okay,
Donna,
so-
silly
yeah.
question. Is it possible to sort of name or classify the pieces themselves? Like call the thing which looks like, you know, the circle with the two things. Like,
I am really bad. Like I only called them like the orange piece, the purple piece, the red piece. I didn't make up real names for them. So I'm sorry about that.
no. I would think because
So
like,
every piece is different. So every single piece is different.
right. I noticed.
And the only one piece has symmetry. The rest of them don't have any kind of symmetry. So sometimes I call that purple piece the symmetric piece because there's another purple piece. But you know, when you're doing research by yourself, you don't need words to describe certain things. Okay. So yeah, so that seemed to be a dead end. Although I ended up using this idea again after my algorithm was quite a bit more robust and already solving puzzles, then I added this in. But I was very frustrated because I thought this insight should give me more leverage than it did. So I needed a model so that I could program it into the computer. And this is what took me a really long time because this is what the board looks like. And I was like, how am I going to code that up? That doesn't make any sense. Like, how do I put that in a computer? And I kept thinking in my mind's eye that I wanted something that looked kind of like this, but that doesn't work because when it would tell you where the anchors are, it would tell you where the balls are. But I kept saying, but you know, the angles, these things come out at all different angles. So how am I going to code that up? And finally, like one day it just hit me like a ton of bricks, like this is what it should look like. And once I came upon this model, everything was great because like now I can actually code this up. So even though in this picture, it looks like there's trapezoids, those are actually hexagons too. They're all hexagons. And if I make the anchors yellow and then stretch this picture, I end up with this picture. So this picture, the little tiny black spots are little points you can't reach on the board. They just don't exist. They really are just like empty spots on the board. You can't get there. You can't put anything there. But in my model, I stretched all the hexagons out so they were the same size. And so those black points are just unreachable in my algorithm. But the yellow points are the anchors and the gray spots are where the rest of the pieces live. So if you look at the published diagrams versus mine, they're kind of skewed because of the way I did that. But does that make sense? I'm gonna wait till Aleka nods and then I'll go to the next slide.
I'm not sure I get it, but
okay, let me just show you again. So in the original board, there's these little spots that don't really mean anything and you can't really see them. Like they're just little empty spots on the board. But I want to be able to, for example, the sockets either fill up 5 of these 6 spaces around the anchors, or the wide socket only fills up 4 of them. Okay, but by doing this, I was able to specify like where these spots are filled up. And so like if the diagram on the left, you see like this is a full circle. And so I cover up the anchor and the 6 points around it. But for example, this socket opens to the lower left. And so I fill in these 5 hexagons and then the other piece fills in. So where you see a huge ball, it's a single hexagon filled in. So it's an artistic shift so that I can model it in the computer.
yeah, I could see that.
Okay, cool. Anybody else have any questions or should I move to the next slide? Okay, hearing nothing, I'll go to the next slide. These are my game pieces. And so I just labeled these with zeros to indicate that that's where I chose to put my anchors. They could have been in other places. They didn't even have to be where there was any plastic. For example, in this pink piece, I could have put the anchor right here, or I could have put the anchor right here. But I chose to always put the anchor where there's a physical piece of plastic because it just felt, this is my human prejudice that I shouldn't anchor where there's nothing physically there, but it really didn't matter. I could have anchored in any one of these. So each one of these pieces, you'll notice, has 3 potential spots where I could have anchored them. So each piece has to somehow interact with 3 of the anchors on the physical board. Does that make sense? So since they interact with 3 separate anchors, it's kind of arbitrary which one I label as the main anchor. Okay, and then I address the board using orthographic coordinates. And I decided if you want to hear more about that, that'll be questions and answers, but I'm just going to kind of breeze past this. This is what orthographic coordinates look like. They're a lot of fun. You can write them as 2 coordinates or 3, but if you use 3, the third one is redundant. So in calculations, like in the computer, there's no reason to use a triple. I just use a double. Anyway, so in order to figure out where the pieces go, each piece is made up of several points relative to their common anchor. So when you just change the anchor by addition or subtraction, and then you decide whether you want to flip it or not, and you want to rotate it or not. So a typical piece has 12 possible orientations, and I numbered them 1 through 12, and I numbered them so that the even ones are all of the same chirality, and then the odd ones have the same chirality. So you can kind of see what they look like that way. Does that make sense?
Mhm.
Okay, so my code is in Python 3. I import a lot of stuff so that I can draw pictures, and then a lot of stuff so that I can just do calculations. So my initial strategy in my code was to do something that I can't do as a human. So I wanted to use my code to give me insights into things that I couldn't just do manually. So I decided I wanted to tabulate every possible placement for every free piece in the game. Now, clearly there's only if there's only one possible placement for a piece, that has to be where it is. And then if you do that, then that piece is no longer free and you've reduced the puzzle by 1 degree. And so I was wondering, by this simplistic process, and back to this whole Sudoku question, how many puzzles can I solve by just repeatedly using this algorithm that is very easy for a computer and very hard for a person? And it turned out that 21 of the 120 puzzles were completely solvable by just using this process repeatedly. And it even solved one of the puzzles that's labeled as expert. And so I was a little bit disappointed, but I'm glad because it showed me that I had to go further in my strategy. And let me just say, my algorithm is at its core recursive and brute force. And I'm not thrilled about that. But what I do is I optimize the lineup so that I try to find out which moves are more likely to be correct, and I make those moves first. And that's what accelerates the solution to the game. Accelerates my finding of the solution is the optimization of that brute force recursive algorithm. Okay, so this is a audience participation coming up. So the next technique I use is called basic pairwise cleanup. So if I have, let's say I have 3 pieces and each of them could be placed on the board in 2 different ways. So I just give them each different numbers for convenience. So let's say the green piece has one of 2 possible ways it can be placed. I'm calling it placement 1 and placement 2. The red can be, you can use placement 3 or 4 for the red, and you could use placement 5 or 6 for the blue. But the edge, when I draw an edge on this graph, it means that those 2 placements are mutually possible. So example, I can put down the green in position 2 and the blue in position 5, and they don't collide with each other. So given this graph, can you eliminate one of those 6 options so that I can clean up this graph and move forward? Anybody? Michael's not allowed to answer this one because he knows the answer, but somebody else has to answer it. So I'll give you a hint. 3 is not possible. Can somebody tell me why 3 is not a possible placement?
It's inconsistent with any of the greens.
Correct. 3 is inconsistent with any green placement, so it can't be part of a solution. Also, 6 is impossible because it does not connect to anything green. So if you're thinking about this in terms of graph theory, I'm looking for a K3 graph because I have 3 pieces I need to place. So a K3 graph in this case is just a triangle. So any piece that isn't part of a triangle graph, or I'm sorry, any placement that's not part of a triangle can be eliminated. Okay? All right, then the next thing I did to optimize my algorithm is something that you would kind of naturally do by hand. It would not take any extra effort for a person to do this, which is this idea of useless placements. The placement I've made on the left is completely useless and should be replaced with the placement on the right. And the reason is the placement on the right is more flexible and allows more moves, whereas the placement on the left is less flexible and could never be part of a solution because the author has promised us unique solution. If the placement on the left were part of a unique solution, it's not possible because you could simply flip it and you'd get the position on the right. Okay, so there's a whole host of placements that are completely useless and can be easily replaced with a better choice. And so I tabulated those and made sure that I never allowed the puzzle to use those placements. Does that make sense?
Mhm.
Cool. All right, so then the next thing is, so every time I made one of these adjustments, I would try running the code and something would go a little better. Sometimes it wouldn't speed it up very much, but I just would leave it in. Okay, so maybe it helped a lot, maybe it helped a little. But every time I got some new solutions that I didn't get the last time, I would get excited. And the other thing is, in theory, I should have been able to solve any of these at any point. But the thing is, I just am not very patient. So if my code is running for 10 minutes, I'm just going to stop it and say, like, forget it. You're taking too long. Let me try to optimize my code. All right. So this heat map sorting is a very common strategy you'll use in some kind of programming environment. And since the computer can quickly figure out all possible placements, it can also overlay them all on one board and create a heat map. The portions of the board with less coverage are considered to have a higher priority in the heat map. So I sort the possibilities using the heat map so as to prioritize my brute force algorithm. So the first thing I just want to show you is the overall heat map for the entire board. So as you can see, there's a lot more pieces that can exist in the center of the board. And the hardest places to put the pieces are in the lower right and the upper left corner. Of course, there's a symmetry to this board. You can flip it upside down and you get the same board again. And of course, all the pieces can be flipped upside down. So it would be crazy if this were anything other than symmetric. And of course it is. I'm going to show you 3 different puzzles just as an example to show you what the heat maps look like visually. And in each of these 3 examples, the original puzzle is going to be in the upper left. The solution to the puzzle is going to be in the upper right. And the heat map, which was generated by the puzzle, is beneath the solution. Okay, so these three diagrams will be in that configuration for the next 3 slides, right? So for puzzle 25, it's one of the early puzzles, and the heat map tells you exactly where the pieces have to go. This is the most basic example because you run through the heat map once and it's like, there's the pieces. It's kind of like a dead giveaway because the heat map is a silhouette of the solution. Everything can only go in one place and it has to go there. Just like when we did puzzle 1, it would have looked the same way. Okay? Is that clear? Okay. All right, puzzle 40, you can see there's a little more complexity. There's some heat in the lower right corner because all these pieces can kind of squeeze. If you look at the original puzzle, like that 934 zone, all the pieces can kind of squeeze in there one way or another. But the heat map still reveals to us that there's only one place that can, there's only one piece that can be received between anchor point 19, 20, and 21, there's only one piece that fits nicely in there, and that's our symmetric piece. That's our purple piece. And so actually what happens in this case is the algorithm will place that piece first, and then it will run the heat map a second time, and then it will come apart pretty easily because once you get down to 3 pieces in my algorithm, it just usually solves it very, very quickly. It's not very difficult when there's only 3 options. You can just brute force it from that point, and it's trivial. But the heat map also will reveal quite a bit at that point. But I just wanted to show you what it looks like when you start transitioning from the simplistic problems into the slightly more complex problems, okay? And still not very complex, but to show you again the structure of how these heat maps develop. When we have puzzle 85, remember there's 120 puzzles. So puzzle 85 is quite difficult for a person who hasn't done a lot of these. And if you look at the heat map, it's still kind of telling you where this purple piece should go. It's kind of hinting that that's got a really high priority because it's very bright blue over here. This pink piece is probably what goes here, and this heat map is telling you that pretty much. And then this turquoise piece probably goes down here. Its structure is going to look a lot like this green piece over here, but since this green piece that I'm pointing at is already part of the original puzzle, it's going to tell us that probably the turquoise piece is the one that goes down here. So there's a lot of clues even in this heat map, but you can see that there's more red and there's more ambiguity as the puzzles progress in difficulty. Okay, so what comes next? So I implemented the heat map and I still came up against a brick wall. I got a lot of solutions that I didn't get at the previous level, but I still had quite a few puzzles that were just really hard to crack and I couldn't get through them. It was just taking too long, and I would just, you know, after several hours, you just kind of quit. You just tell the computer, stop, I don't want you to do that anymore. And so this last condition I added to my code actually allowed me to solve all the puzzles finally. And this is the part that seems effortless on the human side, but it was a lot harder for me to implement. And the key insight here is that at any point in the gameplay, if you're on your way to a solution, there are some remaining legal moves that are immediately linkable to the existing structure. There's also always some correct moves remaining. And at least one of the remaining moves is both correct and linkable. So it's both legal move and it's actually part of the actual solution. So the question I had was, what if I do this thing on the computer that I naturally do by hand, which is I try to build on the existing structure. So for example, look at these 4 pieces in this puzzle. Like there's 4 pieces as part of the original puzzle. And I've just made, in dark gray, I've shown you 2 of the various pieces that eventually have to be set down as part of the final solution, okay? The final, yeah. So in order to do this computationally, I just want to know, should I just only look at this? This is actually that purple piece that's symmetric. Should I only allow that and other pieces that link immediately, or should I allow all legal moves as part of my search space? And it turns out to be tremendously helpful to only permit the computer to pick a move that is linkable to the existing structure. So that actually sped everything up tremendously, and that really kind of surprised me. And it happened roughly around puzzle 50, so just before the midway point in the puzzle lineup. So before that point, so for the early puzzles, it takes more time than it should, in a sense. Like searching with linkability gives you, like, there's a surcharge on that, but once you get to around puzzle 50 or so, then that surcharge is something you're happy to pay for, because the puzzles get much more difficult to solve.
Donna, I have a quick question.
Yeah, sure.
There's this idea in programming that I use a lot in signal processing called dynamic programming. It goes back to Bellman, is this gentleman Bellman, and it's basically sort of like a discrete form of calculus of variations. And what you do is you make a decision, but then at that point in your algorithm, you then have a cost for making that decision, and you sort of trace it out and you get an intuition about whether or not that's a correct move or not. Would that kind of a strategy help you with this? Or like, let's say you reach this point in the puzzle where you have, you know, these ambiguities, and sort of play them out for a little bit and then see the cost effectiveness of that. And then this system is rather simplistic, because I can just count how many pieces are on the board. So if you see with the number of missing pieces, right,
it trends upward. The number of missing pieces trends upward with the difficulty of the puzzle. So it's a good proxy for the puzzle difficulty. So I would say, if I were doing something naive, I would say if there are 6 missing pieces, I should use linkability. If there are 5 or fewer missing pieces, then it's not going to help me. That's probably where I'd make the cutoff. But because it's a simplistic system, I don't think it would make more sense. It would not make more sense to go deeper into it than that, just because again, there's only a total
Right.
of 12 pieces in the puzzle.
You can run all your models anyway, so you don't need this kind of.
Yeah, like I was really hoping, honestly, that I could generate new puzzles with my algorithm, but it becomes so computationally intense. Like my holy grail, which I never got, was can I just find all the possible configurations that fit into this tray? I really have no idea how many there are, because I know there's 120 puzzles, and then there's the configuration on the front that isn't a solution. But I would really love to know all the possible configurations, but no such luck, because the computational investment goes up like, you know, n squared, n cubed, n to the fourth, n to the fifth. And so like maybe I can handle an n to the eighth problem, but that doesn't mean I can handle an n to the 12th problem. You know, so it just goes up so astronomically fast that I would love to talk to Ralph Peters and actually ask him if he has answers to these questions. But I think because it's he's a proprietary game developer, he didn't publish anything about this puzzle. So that's why I'm like, hey, I guess I got to figure it out myself.
Well, thanks.
Great. Okay. So my computation time, I ran this not on my laptop. I ran this on Robinson's computer up in his office on his remote machine, so that I could just leave it and come back later. And I think it took roughly 2 weeks to run everything, maybe not quite, but the longest solution took a full 7 days. I ran it twice. I ran 2 different variations of my algorithm. The 3 and the 4 is at what point I brute forced the rest of it. But it didn't seem to make much of a difference. But the puzzles that my algorithm found difficult, it was difficult whether it brute forced it 3 pieces remaining or 4 pieces remaining. But this graphic doesn't really make sense, because we don't think that, like down here, you can't see anything. These all look the same. So I'm just going to plot this on a log scale. And like, what is log 6 anyway? So what this means is like 1 second is down here, 2 minutes, 1 day, 1 week. So that gives you a better intuition of how long it took to solve some of these problems. So you can see like everything around like puzzle 40 and below, we're talking about click enter and the thing is solved. Whereas like when you get around to puzzle 80, you have to go, get a glass of water while you're waiting, right? And then by the time you're over at some of these spikes, it's like, okay, it's going to be a week before this is done. But also by plotting it on a log scale, it doesn't look like those spikes are quite as meaningful anymore. The spikes just seem to be part of the noise in the log scale. So anyway, that's what that looks like. And I highly recommend this game. I feel that the game changes as the levels progress, like you grow with the game. I do not feel like it's just trial and error. I feel like I'm feeling myself develop strategies as the game progresses. And anyway, if you're looking for something inexpensive for the holidays, it's really a nice thing a mathy thing to give to your non-mathy friends and family. Okay, anyway, you guys all know who I am, but that's just my how to find me slide.
Great, thank you very much.
Excellent.
There is a question for you. I can see on the chat from Jeff. After you have tried placing a few pieces, do you generate a new heat map or not?
Yeah, I do. Yeah. I generate. This can be tweaked, but it's been a year and a half since I wrote it. But I believe I generate a new heat map at each iteration. You could also just generate one heat map, but I think the thing is, as you place a couple pieces, the game changes quite dramatically. And again, if you have an order, n to the 8th problem, and you place one piece, you now only have an order n to the 7th problem. So it behooves you to go ahead, and the calculation 1 level down is much cheaper than 1 level up. So you may as well create a new heat map, because that's really fast for the computer. If we were live, I would literally pass this thing around, because when I gave almost the same talk, I gave it at MoMath a year and a half ago, and I had a couple copies of this game, and I passed it around, and people were having a grand old time playing with it. So I'm very sorry that I don't have a game for you. And since it's copyrighted, I can't just make a game and put it on my website for you because I think that would be a copyright violation. So sorry about that. But that's why you have to just buy your own.
Good suggestion. Any other questions for
We're not live, Michael Case. I do have a toy. If everybody is like, oh, I really want to play with the toy, I have a toy that's completely different that I can give you. An electronic toy. So if the questions run out before the hour, I'm just going to give you a different toy. But you've seen it already, Jeff. Somebody's got to have questions.
I don't have a question. I just have an observation that it seemed to me amazing that with just 2-3 pieces, you could find a unique solution.
Oh, I know. That blew my mind. Oh my gosh, I really don't know. That's why I really wish I could have this. I wish I could find every single valid configuration and then actually have a better understanding of, are there 2 configurations that have the same placement of any piece? Like some piece has to be common to 2 configurations. So how many pieces do you need before it's a unique a unique solution, or does that change? I mean, I want to know if there's something more fundamental about what's going on here, since every piece is different. Does it each piece has its own role, so to speak? I don't really know. And then it's just it's still a mystery to me, even though I've learned so much. And at some point when I was creating the code, at some point I said, look, you finally just got your code to solve all of them. And I still didn't feel satisfied. Like, I really want to know more about this puzzle. I want to know all the configurations and what causes a puzzle to have a unique solution. But I will make this comment that when they published the first edition of the game with the first instructions, there were some errors in the answer key. And how can there be errors in the answer key, you might ask? But there were some puzzles that have more than one possible solution. So that's a partial answer to my one question. Is it possible to have a puzzle with more than one solution? And the answer is yes, but it was an accident for them. So like you could accidentally create a puzzle that does not have a unique solution. So that's something you can do. But they have promised us that they fix those problems and that now every puzzle that's listed does have a unique solution. So I don't know whether that's something they did theoretically or it's something that they just brute forced it on their computers until they proved that there were no possible other solutions. I don't know. Because my code stops as soon as it finds a single solution. It relies on the promise that the solution is unique. Otherwise, the code would still be running.
Right.
Like 2 years later.
We have one more question. Is there a possibility of smaller versions of the puzzle? Or is this...
I have no idea, right? That I do know that there are other games by the same puzzle designer, but they're different geometrically. A lot of them are like balls, like they're 3-dimensional ball and sockets, and you build pyramids and things like that. There's all different things. I am attracted to this particular game in part because of just the beauty of the pieces. The pieces are just so much fun, and when the sunlight comes and hits them, they shine all over. And that's part of what I like about the game, which has nothing to do with the mathematics. But again, I think I'm more attracted to the hexagonal grids, and a lot of this puzzle lists, a lot of Raph's puzzles are on a Cartesian grid. And so to me, that's, for whatever reason, I find Cartesian grids less interesting than hexagonal grids. This is my prejudice, right? But I don't know if it's possible to make a smaller version.
Okay. Any other questions for Donna? Thank you very much, Donna. Very good talk. Thank you.